Hey guys, I'm here in my classroom. There's nobody else here, so I'm not wearing a mask. But um, I am making this video for those of you who were not able to do the lab in the gym, where we experimented with dropping a basketball and a tennis ball simultaneously. And we did this several times. We measured how high they went. And then we made a data table with that information. So I'm going to give you that stuff now. And then we made an energy diagram showing what was happening with the energy here. So to start with, we measured the basketball dropping by itself and the tennis ball dropping by itself. And we did that in a previous video from last year. I think I'm wearing a face shield and stuff. It was when we first came back after COVID. So those pages of the project, let me see. I'm looking at the project over here. Let's just see. Pages 1, 2, and the first half of page 3. Let me show you. These were done on that other page. So I'm going to switch over so you can see this screen. On that older video, I described what was going on with the title here. The title being Conservation of Energy. And I'll tell you right now, there is a test question where you need to describe the 3 parts of the conservation of energy. And you might have heard this already because there's a similar law called the conservation of matter. And both of them say the same thing, except one's about matter and this one is about energy. 3 parts that I want you to be able to tell me. Part 1, energy cannot be created. Part 2, energy cannot be destroyed. Part 3, but energy can be transferred. We can move energy from one place to another. So we can't make any new energy, and we can't actually destroy any energy either, but we can move it from point A to point B, or from object A to object B. And so to demonstrate the conservation of energy, we're going to be working a lot with these 2 types of energy shown in this equation right here. ME equals KE plus PE. KE is kinetic energy, the energy of movement. Potential energy is stored energy because of an object's position. So if I take this basketball, right now, it has potential energy because it's off the floor. It has the possibility, it has the potential of falling down to the ground. Up here, it has more potential energy. Just imagine, wouldn't it hit the ground harder if I dropped it from here than dropping it from here or dropping it from my knees? When it's on the ground, it has no potential energy left. Okay? Now, kinetic energy and potential energy are always being transferred back and forth when things are moving, especially when they're going uphill or downhill or falling. And together, we call these 2 types of energy, when we add them together, we call them mechanical energy. So mechanical energy equals kinetic plus potential. And this helps us calculate how much energy there is and how much has been transferred from one thing to another. And so the third thing you'll see on this title page is that it is going to focus on developing models. And our models are really going to be diagrams that help us understand what is happening in these energy transfers. Okay, so the first video tells you more about that. It tells you about the background photo, which is a photo of the Orion Nebula. And there's more about Orion on this next page. Again, this is in the first video. You'll see it says part 1 on teams. Then the second video really should have allowed you to fill in this top half of this page. So on here, if I zoom in a little bit, you can see that you should have done a few things. On the left are the instructions. On the right are where you need to fill in some answers based on what happened in that first video that I've posted on Teams. So we're going to measure how much a basketball bounces when you drop it from 1 meter high. So I'll just remind you, this is 1 meter. It's slightly more than a yard. But the great thing about the meter is that it's divided into 100 parts. So it makes it so much easier to do math than like a yard where you have to divide by 36. That's kind of awkward and inconvenient. This is one reason scientists much prefer the metric system, because it's all done by tens and hundreds and thousands. And all you have to do is move decimals around to make conversions. At any rate, we dropped the basketball from 1 meter high. We measured its bounce. We did the same thing with a tennis ball, dropping it from 1 meter high, measuring how much it bounced back. I did that in the other video. Then we did a combined one. And notice here where it says B plus T bounce predictions, basketball plus tennis ball. When it says plus, I'm talking about dropping them simultaneously with the tennis ball balanced on top of the basketball like this. And I showed that in the other video. Much to my surprise, when I first did this, the tennis ball went flying. So that leads to this question, why did that happen? But of course, this is asking for a prediction. You're not supposed to know that before you predict. So what I wanted for the prediction was for you to just say if you thought the basketball will bounce higher, not as high, or the same as when it was bouncing by itself. Similarly, what did you think the tennis ball would do? Would it, basically, there's 3 choices. Bounce less, did it bounce more, or did it bounce the same as when it was by itself? So we have these alone measurements, and then we have these combined measurements. Okay? So, hopefully you already completed that part of the project up to where it says B plus T bounce measurements. What we're going to do right now is I'm basically just going to provide this data for you. Okay, this is what we did in the gym. I had to climb up on a ladder and set up a big poster that measured how many centimeters it was off the floor. And it was, I don't know, 15 feet tall. Actually, I should say it was 4 meters tall. So 4 of these. I was pretty far up there on the ladder hanging that thing, and I've already taken it down, so I can't really redo the lab directly with you, but I can give you data to work with, okay? So, again, this top part, you should get these from the previous video. Right now, we're going to fill in this data table. So where it says each 1 meter, that's when the basketball bounced by itself. And the tennis ball bounced by itself, where it says each. Where it says both, that was when we had them dropping at the same time. Okay? I don't know how well it'll do, but let's just see it. You're not going to be able to see the whole drop. You might see the tennis ball fly up when I drop these together. Well, it flew off to the side. That kept happening. If it flew off to the side, we would actually refilm the entire thing. What I mean by refilming is that every student had their camera out, and in slow motion, they filmed the ball dropping and bouncing back so that they were able to measure how high it bounced by seeing when it hit the top and then when it came back down. So we drop the ball, they'd have their slow-mo video on, the ball comes up to here, and they could tell by looking at this meter stick in the background, we measured from the bottom of the ball that it came that far. So that would have been a 75 centimeter bounce. So by using a video, we were able to get a pretty good measurement of these things. The tricky part was, like I just showed you, sometimes this ball went off to the side. What we really wanted was for it to go straight up. So we did it multiple times, maybe 10 times, and then we took the 3 best measurements to record in this data table here. So let's go ahead and work on the data table. So when the ball was dropped by itself, it bounced back about 62 centimeters. Meanwhile, the tennis ball bounced back something like 37 centimeters by itself. That kind of surprised me a little bit too, that the tennis ball bounced back less than the basketball. Then we get to the point where I dropped both of them simultaneously. And this is the kind of data we ended up with by looking at these videos. The basketball, when it had the tennis ball sitting on top of it and it hit the ground, that ended up bouncing less than it had before. So just to make some numbers, approximate numbers, 32 centimeters on the first trial. On the second attempt, 41 centimeters. And on the third attempt, let's say, again, I'm just estimating these. I'm kind of making them up, but I know the approximate values that they actually were. Let's say that was, I don't know, about 30 centimeters. Meanwhile, when it was dropped perfectly straight so that the tennis ball shot straight up instead of shooting off to the side, when it did that, we had some kind of, I think, amazing results. We had like 240 centimeters, 210, and 260. Let's call it 265 just to make it interesting. Okay. So this is what we did in the large gym one day. We did 2 different labs in there. Excuse me, it was the small gym. But one day I did all the dropping of these balls together like this. And students filmed it, and then we measured how much they bounced back. Okay? So your next task is to find these averages. I'm not going to do this for you. I want you to do it for yourself. Hopefully you remember that finding an average is not too hard. You just add the numbers together and then divide by however many numbers there are. There's only one tricky thing here, one potentially confusing thing, which is we're only going to average when we drop them together, right? We're not going to include the solo bounces. We're interested in the average bounce when I drop them together. So ignore that top line. That's why I put a line through it. Don't you put a line through it, but don't include that when you do your math. So for the first one, for the basketball, you're going to put into your calculator 32 plus 41 plus 30, hit the equals sign, and then divide by, let's see, how many were there? Oh, there were 3. 3 numbers that we're finding the average. So divide by 3. One way you can tell for sure that you got a good answer is that your answer had better be more than the smallest number and less than the biggest number. So if you got a good average, it was between 30 and 41. Any more or less than that, and you did a mistake in your math. Sometimes people forget to hit the equal sign before they divide, so watch out for that. Then do the same thing to find the average for the tennis ball bounces. Add those 3 numbers. Since there's 3 of them, divide by 3. Now, if you haven't finished that math yet, pause the video and then come back, but I'm going to keep going. So the next thing we're going to look at is what we call an energy diagram. And you see these two blue rectangles. And it's pretty obvious. There's a big rectangle and there's a small rectangle. And these are going to be used to model the amount of energy in the system. The bigger the rectangle, the more energy, and vice versa. We can also use different symbols to show different kinds of energy. Like here they're blue, maybe that's representing kinetic energy. We could also use orange to represent potential energy, things like that. Let's move on to the next page. Okay, so here we're going to model that basketball bouncing. We're going to do it twice. You can see there's two sides to this diagram. On the left is our prediction, and on the right is what actually happened. Okay, so let's look more closely at that. I'm going to zoom in on the prediction, the bottom left. So here I have the basketball and the tennis ball, one on top of the other, and you can see that they're falling down from 1 meter high. They hit the ground and then they bounce back up. This is where I'm supposed to make a prediction of how high I thought they would bounce up. So what I'm going to do is I'm going to draw a circle to represent the basketball. I'm going to try to make it about the same size as it was over here. There we go. And then I'm going to move it where I want it to be. Try to move it. There we go. I'm going to show it. I'm going to predict that it was going to bounce up about that high. So I'm going to end up covering this arrow up, but that's okay. I also want to make sure that I remember this is a basketball, so I'm going to change its color. To do that, I'll remind you, you click on the object, right-click on the object, hit Properties, and then this comes up. This color would change the border of it. This color would change the center of it, the fill. So it was a basketball, so I'm going to make it orange. Makes it really obvious to me that that's what I'm thinking about, is how high the basketball was going to bounce. Then I'm going to do the same thing to represent a tennis ball. But of course, I'm going to make it green. I'm going to try to make it about the same size as this one. It doesn't have to be perfect. So let me see. Click over here, click over here. When this turns into a little arrowhead, that's when I'm able to move it easily. I'm going to line it up, and I'm going to predict that it was going to go this high. I don't know how high you predicted. You placed the basketball and the tennis ball so that they match your prediction. I didn't think the tennis ball was going to go that high. Once again, I'm going to change its color. Change the fill color to this green so it looks like a tennis ball. And there they are. That's my prediction. Now, a minute ago, I said that your prediction needs to match. So here's a diagram of my prediction. It's like a two-dimensional model of what I expect to have happen. And it should match whatever numbers I wrote down on the previous page, specifically right here, where it said these predictions. What were you predicting to have happen? Whatever you predicted, your diagram should show that same thing. And I want to remind you, on a prediction, it's what you think will happen before you actually do the measurement. So hopefully you've already done it because you've seen our data. And that kind of gives you a bias instead of having an honest prediction. So it doesn't matter if your prediction is right or wrong, because we always learn something from making a prediction in advance. It just is asking you to think about what you expect to have happen. And then we can make a nice comparison. In fact, I kind of like it when people have an incorrect prediction, because then it makes it really obvious that they learned something. But at any rate, whatever your prediction is on this page, it should match this first diagram that we've been working on here. Now, I didn't predict that the tennis ball was going to go very high. And actually, I think I would have expected the basketball not to go that high either. So I'm going to move my basketball back down here. And since I've covered up the arrows, I'm going to make new arrows to show the basketball bouncing up to there. That's pretty hard to see. I'm going to change it to a black arrow. Once again, I hit properties. There it is. Then I'm going to make a second arrow. Easiest way to do that is to copy paste. Remember, Control C, or if you have a Mac, Control Command will copy, and Control V will paste. There's my prediction, right? So you're going to do the same thing. If you need another minute to work on that, again, this is a good time to pause the video, but I'm going to move right on to the actual measurement, okay? So the first thing I need to do in the actual is show, once again, an arrow that the balls are falling down to the floor. So I'm going to paste another arrow on there, but I'm going to flip it over so it's pointing downward to show that this is the movement of the ball to begin with, moving in this direction. And then it hits the floor, right? So I'm going to make yet another arrow showing it bouncing up. Again, I'm able to make those arrows so quickly because I did copy paste. Instead of having to draw them each time, I just do copy paste, and then I can move them where I want them to be. I'm going to do the same thing right now with both the basketball and the tennis ball. So now this measurement needs to match whatever we came up with in the data table. And I'm not necessarily going to put this in the exact right place, but I want you to put it in the right place. It should be this number right here where you calculated the average. Whatever you got here, and I can see that it should be more than 30 and less than 41. Whatever you got there is what you're going to show in the diagram for the basketball. Same thing for the tennis ball. Whatever you calculated over here, that should be your answer for the tennis ball. In your diagram, that's what you should show. Okay, so let's see. This is 1 meter. I think there's 1, 2, 3, 4, 5, 6. So 3 lines would be half of a meter, wouldn't it? 3 of these boxes would be half a meter? Yeah. So that means the bottom of the basketball only made it up to about 30. I think I actually have to lower this a little bit to make it a little more accurate. Then I need another arrow to show what the tennis ball did. I'm going to take this arrow and I'm going to put it here. And I'm going to stretch that arrow upward. I don't remember how far. I better go check on the previous page. Where am I going to draw that tennis ball? Let me see. It is the average of these 3 numbers, somewhere between 210 and 265. That's where I need to show my tennis ball. So I'm going to go down here, copy paste the tennis ball, Control C or Control V. There it is. I'm ready to drag it to where I want it to go. I find it much easier to click somewhere else. Then when I come back to it, it's easy to drag. Now I want you to notice this says 2 meters, right? But I'm looking for 200 and some centimeters, huh? That's what we measured over here, was 200 and something centimeters. Well, remember, 1 meter is 100 centimeters. 2 meters is 200 centimeters. So when I'm looking at my diagram, it says 2 meters, but I'm thinking in my mind 200 centimeters is where I show the ball right here. But I know it was more than that. It was in the range of, I don't know, something up here. There's my tennis ball. I'm going to go ahead and grab this arrow and stretch it out all the way there. And now I have a model of the bouncing of the ball. Both my prediction, what I thought would happen on the left, and to my surprise, when that tennis ball went flying and hit the ceiling in here on the right, what actually happened. So at this point, your paper should look something like this. And there's another thing we have to do before we're done. So once again, if you're not at this point with me, pause the video for a minute and then come back when you're ready to go on, because I'm moving on to a new topic. So now we're going to talk about those energy diagrams. We're going to diagram the amount of energy, and we're going to show the energy transfers that happened during this ball drop. And if you remember, we're showing the amount of energy just with rectangles. The bigger the rectangle, the more energy. And I want to show a rectangle for before the balls were dropped, which will be all potential. And then I want to show another rectangle for after, measuring how much they bounced back. It almost looks like the tennis ball created energy, doesn't it? But wait a minute. The energy law says you cannot create energy. So what happened? How did the tennis ball end up flying so high if it's impossible to create energy? It got that energy from somewhere. So where did it get it from? Hopefully, thinking about this guy. If you look at what happened, the basketball seems to have lost energy. Was that energy destroyed? Absolutely not. You cannot destroy energy. If we go back to the data table, you'll see what I'm talking about. By itself, I'll get rid of this line because we need to look at these now to make these comparisons. By itself, the basketball, it says it bounced 62 centimeters here, right? But look, it didn't bounce that high when it was bouncing with the tennis ball. It looks like some of the energy was destroyed. Meanwhile, the tennis ball only bounced 37 by itself, but it bounced 200 and something when it bounced with the basketball. It looks like energy was created for the tennis ball and destroyed from the basketball, but that did not happen, did it? What's the law of conservation of energy? You cannot create energy. You cannot destroy energy, but you can transfer energy. So what happened? Energy from the basketball was taken away and given to the tennis ball. And because the basketball is so much bigger, a little bit of energy that it had translates into a lot of energy in the tennis ball. No creation of energy, no destruction of energy, only transfer. From the basketball, it lost energy. Tennis ball gained energy without anything being created or destroyed. That means when we do our energy diagrams, the total amount of energy should stay the same. The total that we start with should be the same as the total we end with. But the amount in the basketball should be reduced, and the amount in the tennis ball should be increased. So we're not going to actually measure these numbers. We're just going to kind of fudge it to represent what happened. So to draw our energy diagrams, I'm going to do two of them, one for the before and one for the after. And I'm just going to draw a rectangle to represent the energy in the basketball to start with. And I'm going to make it the same width as this grid on the graph paper and the same height as the basketball is to begin with. And I'm going to change it to orange so it shows that this is the energy in the basketball. Oops, I changed the line. I want to change the fill, Forgot. Got to change the fill color to orange. There we go. So I believe if I counted correctly, that is showing 1, 2, 3, 4, 5, 6 boxes of energy. Well, we don't measure energy in boxes, we measure energy in joules. So here I have 6 joules of energy in the basketball before I dropped it. That's all potential energy. Meanwhile, I'm going to draw another rectangle to represent the energy in the tennis ball. And I'm going to make it be 1 box in size. I'm going to change its color to match the color of the tennis ball. Click OK. Now the last thing I have to do is drag this box down to where the tennis ball is. Okay? Because the tennis ball is so much smaller than the basketball, it started with less energy, even though it was slightly higher, but its mass is less, so it had less energy. Right? Please take a look for a second. How many total joules of energy did this system begin with? And when I say system, I mean the combined basketball, tennis ball system. A system has many parts that operate together. In this case, they fell down to the ground together, and then they both bounced back. So how much total energy was in the basketball, tennis ball system using our way of measuring energy as boxes? It seems to me that before there was a 7 joules of energy. Remember, joules is the measurement of energy named after a scientist, Dr. Joule. And before we dropped the ball, there were 7 joules of energy. 6 in the basketball, 1 in the tennis ball, a total of 7 joules. Now I'm going to copy and paste this box, Control C, Control V. I'm going to drag it over here to do my energy diagram for after. And as you know, the basketball ended up with less energy. I'm going to just say that it was 3 boxes of energy now. Meanwhile, the tennis ball took that energy away from the basketball. While the basketball lost it, it was transferred to the tennis ball. And if I do my math correctly, copy paste the tennis ball energy diagram, drag it over to next to the tennis ball. Now it has 2, 3, 4 boxes worth of energy. Now let's do the math. What's the total energy in the system at the end? I do my after label here. What is my total energy in the system? Well, it seems to me that we had 3 for the basketball plus 4 for the tennis ball makes 7. Was energy created or destroyed? No. Was energy transferred? Absolutely. A lot of energy was taken away from the basketball and given to the tennis ball, but the total energy remained constant. This is what we mean by the law of conservation of energy. We're conserving the energy, we're saving it, we're keeping it. It's not going anywhere. Well, maybe it is going somewhere because it was transferred, huh? From the basketball to the tennis ball. When I say it's not going anywhere, it's not leaving the universe. It doesn't all of a sudden wink into existence or disappear into oblivion. That doesn't happen. It's just transferred to another location. And sometimes we can make use of it and sometimes we can't. But the energy still exists somewhere. And that finishes page 4. So again, before we move on to page 5, you might want to pause your video to make sure that you've finished this little section. It should look quite similar to mine. But I'm going to go ahead and move straight on to page 5. And this is a simple thing. It's a page that has some background reading for you and then some questions for you to answer. This is homework that we did. So your assignment is to read this information on the left. And anytime when you're reading background information or reading an article in my class, I want you to highlight the important information. Okay? So highlight the important text as you're reading. There was a really good question in class the other day, which was, how much do we highlight? Because I'll take a point off if you don't highlight enough. I'll also take a point off if you highlight too much. I want you to be kind of picky about what you consider to be important or not important text. And it varies a little bit. But as a good starting point, you should expect to highlight something in every paragraph. Isn't the purpose of a paragraph to show that we have a new topic? And if it's a new topic, there's probably something important to highlight about it. Now, you might also expect that in a longer paragraph, like this second paragraph here, you might expect to highlight more there, and in a shorter paragraph, you might expect to highlight less. Sometimes a paragraph needs no highlighting at all, because it's just an example of something that they've already described elsewhere. And you highlighted the description, so you don't need to do the example also. So sometimes you can skip a paragraph. Sometimes you have to do more than one thing in a single paragraph. Might be really important with lots of good information. So there is some wiggle room in the amount that you highlight, but a good starting point is to think that, oh, I should probably highlight something in every paragraph. So you're going to highlight, and then you see there's questions on the side, blanks to fill in. You're going to answer those. You're done with page 5. Now, page 6 and page 7, this is a lab that I think you should be able to do by yourself at home. We did this on our own, meaning that I provided the materials and we went into the gym or we went into the hall in another class to do these measurements. So it's also about measuring how high balls bounce after dropping them. There's none of them where there's one stacked on top of another, though. It's just comparing how high 3 different balls bounce. Once again, you see in red, it says make a prediction first. So what I want you to do is predict down here on this diagram, which do you think would bounce first? Tennis ball, a rubber ball, or a bouncy ball, or a golf ball? And for your prediction, you just number these. The one you think that will bounce the highest, again, we're not throwing them, we're just dropping them. It's only gravity. There's no force being added on. Same thing was true for that whole thing I just finished talking about. I should have mentioned that earlier. We didn't push them at all. It was just a drop. So here on this page, the only thing you have to do is follow the instructions. You don't have to highlight anything because they're just instructions. It's not background information to read. But I do want you to make a prediction about which of these 3 balls you would expect to bounce the highest. Put a number 1 next to the one that you think would be the winner, the one that would bounce the highest. Number 3 would be the loser, the one that bounces the least. So do your prediction before you do your lab, okay? Then you need to find a tennis ball, a golf ball, and a rubber ball, a bouncy ball, or maybe you don't have those kinds of balls. Any balls will do. You just change things as needed. You could use a basketball and a soccer ball and a volleyball. I don't think a football would work very well because it has such an odd shape, but any round ball should be okay. I don't know if you want to do a bowling ball or not either. That sounds a little dangerous to be dropping that close to your foot. At any rate, what you're going to do is you're going to drop these balls first from 1 meter high, which is about waist high. It's about 3 feet. Second from 2 meters high, which is taller than I am, like 6'6". So what we did to make this work was we took 2 meter sticks. Hopefully you have a way to measure centimeters. Maybe you have a tape measure, and that would work also. And we taped one underneath another. So it looked like this, taped to the wall, one underneath another. Okay, we had these 2 sticks taped one with the bottom of it on the floor. Make sure the 0 is on the floor. And then the other one taped above it, again with the 0 on top of the other one. And then to make this more effective, we also filmed the bouncing of the ball. And so it might help if you get an assistant to help you with this. One person drops the ball, the other person films it. And then if you do it in slow motion especially, you can go back and see just exactly how high did that ball bounce. Did it stop here? Did it stop here? If you don't, you're just kind of guessing where it went because it happens so fast. But with a film, you can pause it. You can slow-mo is really good. You can go forward and backwards. I highly recommend that. At any rate, all the instructions are given on this page. Let's look at the next page where you're going to fill in your data. What I would like you to notice is there are two data tables. The top one is for dropping the ball from 100 centimeters high. The second one, the bottom data table, is dropping the ball from 200 centimeters high, from up here above my head versus down here about waist level. Notice that for each of the three balls, again, it doesn't matter if you have a golf, a tennis, or a rubber ball. If you have different balls, then change the names on there or just put the names off to the sides. But for each ball, you should drop it 5 times and then find the average bounce. Remember, to find the average, add them together, divide by however many there were. Since you did 5 different trials, you divide by 5. Then you do it again from 200 centimeters. Now, if you absolutely need to, you can use inches instead. If you have a yardstick but not a meter stick, or if you have a tape measure that's only in inches and not in centimeters, you can do this in inches if needed. Again, it's much less convenient when it comes to making modifications to our data, to doing the averages, to transferring from one unit, like from meters to centimeters is so easy. To go from yards to inches is tricky. You have to use a calculator. So I prefer the metric system, and we'll pretty much always use it in my classroom. But if you're stuck at home doing this lab on your own and you only have the English system to use with inches, go ahead and do that. When you finish, I think this is actually a total of 30 times you're going to drop the ball and analyze a short little film of it. Notice there's 30 blank boxes, 5 for each of the 3 balls at 100 centimeters. 5 times 3 makes 15. And then the same thing at 200 centimeters. So 15 times 2 makes 30. Then you're going to calculate those averages, correct? After you finish all that data, you start answering these questions. Which ball bounced the highest? That should be easy to answer. Number 2, why do you think this happened? Now that should take some thought. I want you to give a nice scientific answer about why that ball bounced highest. We need to think about physics. We need to think about the characteristics of the ball. So we kind of did some brainstorming in class about the characteristics of the ball. Think about a tennis ball. Inside, it's hollow. But that rubber bouncy ball, it's solid. So that's one of the characteristics that might influence the bounce. How about which one is heaviest? Would the mass influence the bounce? What about the surface of the ball? Like the tennis ball is all soft and fuzzy. The golf ball has that hard surface and it's got all those little dents in it, those dimples. They actually engineered that ball to reduce air resistance, just like an airplane wing reduces air resistance. They design the golf ball to fit that way. What if you were asked to design a ball that would bounce the most? What characteristics would you consider? What about the materials that the ball is made of? All these things, right? So you're going to do this lab on your own. And let's see. Answer those questions. And then page 8 is a diagram of a bouncing ball. Now, of course, when you just drop a ball, it bounces more than one time, huh? So here we're seeing this ball is dropped from up here where it has a bunch of potential energy that gets converted into kinetic energy, right? It falls down to the ground and bounces back, but it does not come back as high as it started. This is a problem because I said energy cannot be destroyed, right? But if it doesn't come back as high as it started, where did that energy go? And it happens again in the next bounce, doesn't it? Hits the ground, bounces back, it comes up even less high than it did before. Every time it bounces, it seems that energy has been destroyed. But of course, we know it hasn't been destroyed, it's just been transferred somewhere. So the question becomes, where did it get transferred? Well, now we have to introduce a couple of new kinds of energy. And these are discussed over here in this corner. When the ball hits the ground, some of its energy is converted into these types of energy. So it starts up here with potential energy. That potential is converted into kinetic while it is falling. When it hits the ground, some of that kinetic energy is converted into these other forms. Let's start with the easy one, I think, is sound energy. It takes energy to produce a sound. So when that ball hits the ground and we hear it, that means that some of the energy was lost. Lost from the ball, but not lost from the universe, right? That energy went off into the air. The kinetic energy was converted to sound energy. It wasn't destroyed, it was converted. At the same time, there's a tiny, tiny amount of heat produced by the impact. It's kind of like friction produces heat. This is called thermal energy, the energy of heat. Now, if there's a little heat produced when it hits the ground, then that would be lost from the ball, huh? And it would be subtracted from the amount of energy that it has. Finally, when the ball hits the ground, it compresses a little bit. It gets squeezed a little bit flat. Let's see, I don't know if you can see this, but this actually happens to the ball on the ground, huh? It gets compressed and then it bounces back. We call that elastic energy. It's another type of potential energy. That's subtracted energy from the ball's fall. One more time. We started at the very top. It had potential energy. Since it's gravity that it's giving that energy, we call it gravitational potential energy. It has the potential to fall. It has all this energy. That energy, when it does fall, that energy is converted into kinetic. Then it hits the ground. And some of that kinetic energy is converted into elastic potential energy. Some of it's converted into sound, and some of it is converted into heat, which is lost from the ball. All of that is subtracted from how much kinetic energy it had, so it can't bounce back as high. It's impossible to bounce back as high as it started from, as you can see on this diagram. Then it falls again. Kinetic energy, oh, it hits the ground. It loses some energy to its surroundings because of thermal energy, sound energy, elastic energy, elastic potential energy. Loses that energy, bounces back up. This keeps happening over and over again until there's no energy left. So your job on this page, and this is the homework from yesterday, is to just describe this diagram in your own words. I just described it in my words. Now you describe it in your words. However, I want you to use all 5 vocabulary terms, all 5 types of energy in your explanation. You should use gravitational potential energy. You should use kinetic energy. Over here, there's 3 more: elastic potential energy, thermal energy, and sound energy. Just so you know, most of the time when I say potential energy, I'm talking about potential energy, things falling and so forth. I'm talking about gravitational potential energy. That's the full name for that. But there's another kind of stored energy, elastic potential energy. My favorite example is stretching out a rubber band. I've put elastic potential energy. That rubber band has the potential to go flying. Another example of elastic potential energy would be like a spring that we compress. It's got energy and it's waiting to bounce back. That's another type of potential energy. Most of the time when we use that phrase potential, though, we mean gravitational potential energy. Okay? So use all 5 types of energy, all 5 vocabulary terms in your explanation. I also highly advise you to use the term energy transfer, or energy is converted, or energy is changed from this to that. You're probably going to want to use that phrase in there a few times, right? Oh, it'd be awesome if you talked about the law of conservation of energy as well, right? Once you've done that, if you finish page 8, you are caught up with the project as of Friday, October 22nd. Okay? So thanks for listening. Let me know if you have any questions. See you later.